So, hi, Boker Tov. So, we're going to have three classes, which are going to cover topics that are somewhat different than what you have so far. You have seen so far. The first topic is inverse problem in computer vision, and the second topic is computer graphics, image rendering, neural rendering. Actually, those two topics were thoroughly studied in the last 2 or 3 or 4 decades by classical approaches, and also other field in computer vision by the hype of the deep learning. They got a lot of attention and good success and progress, since it was shown that it's possible to have very nice results without collecting a huge amount of training data. And although these two topics, as you will see, are totally coming from different fields, they share something in common. And what they share in common, it's the way they represent the signals that are input to the neural network, and the way it's represented, it's called implicit representation. So in order to understand what is implicit representation of signal, let's start and try to go step by step. Any questions so far? Okay, so what we've seen in the course for until now, you are familiar with dedicated architecture for tasks as classification, detection, generation, segmentation, etc., etc. Okay. Our focus today is inverse problem in computer vision. And what do I mean by that? The input to the neural net, or to the process, to the classical approach, is a degraded image. And the aim is to restore the original clean image, okay? So we are going to cover 3 kinds of tasks. One is denoising, super resolution, and inpainting. I know that you are maybe familiar with a few of them, but the approach that is going to be covered today is a different approach. So just move on. Let's move on. So, for example, let's take an example of denoising problem. Then what you get is a degraded image, which actually is composed of the clean image and noise. You don't know the entity noise. And the idea is to move from the noisy image to the clean image. Okay. In super resolution, you get some low resolution image, and you would like to get high resolution image such that the edges are sharp and you don't have blurry regions, like what you see here. In end painting, you have missing part, and the idea is to fill in the missing part that you have in the degraded image. Those are degraded image, and these are the output that you're supposed to do. So far, also in the deep learning era, supervised approach for solving these problems perform very well when they are based on convolutional neural networks. And actually, they are trained over a very large number of pairs of degraded images and their corresponding clean images. And you can guess that it's a huge task to collect such pair of images, collect such training data. And actually, the excellent performance of the CNNs is attributed to their ability to learn from the training data realistic image prior that is useful in order to predict the clean image. Okay? And let's ask the question, is the common approach of supervised learning with large database indeed is the best and only possible way to learn image prior? And the answer is no. You can do something else. Okay? But in order to explain it, let me try to show you what kind of prior exist and how approaches are advancing in this field. Okay. So I guess that you all know what is a prior. For example, in the last 2 lectures ago by Tali in the fusion model, she spoke about priors. I guess that you know what is a prior, but let's try to understand which a prior in the context of an inverse problem. So say you have some low resolution image. Anybody can guess what is going to be the high resolution image? A face, right? So with some imagination, this is going to be the face. And how do you know it? Because in life you grasp some images of faces and you have some knowledge, and actually that's what is called the prior knowledge, with the knowledge about the visual world. Okay. So how to construct a prior? There are mainly 2 categories. The first one is called learned priors by collecting large databases. And the other one is called explicit prior by introducing constraint to your optimization problem. So let's go step by step and understand what do I mean by that. So what are learned priors? For example, in the super resolution case, I take pairs of images, the low resolution, the high resolution, the low resolution, the high resolution. This is the input to the CNN, and you train such that this is going to be the output. In this way, the convolutional neural network understand that the neural net can move from the low res to the high res after learning a large data set of faces, for example, and then in inference you give only the low res image like this, and you get the high res image. Okay. In explicit prior, it's different. You don't have trained data of pairs. You do something else in the optimization problem. You introduce constraint. For example, if this is the input, x hat, and you would like to predict x, then in the optimization problem, you say the following. I would like to predict x such that this is the high-res image. If I'll downsample x to the resolution of x bar, I would like that will have they will be as mass similar as possible, but you can get many high-res images that can let you have this solution, but introduce a constraint. What kind of a constraint? X is the face, X is the natural images, etc., etc. So, for example, how you are going to do it? Explicitly, mathematically, you are going to introduce some regularization like this, and very common regularization. It's called total variation, such that nearby pixels have a similar intensity, and this encourages images to contain uniform regions. Because you cannot naturally express that I want to have a face or I want to have a natural image in mathematical formulation. So over the decades, it was shown that learned priors are much better than the explicit prior due to the limitation of the explicit prior. Okay? But we are going today to speak about a work that did something else. It didn't use learned priors, it didn't use explicit prior, it used something which is called implicit prior. However, without large databases and without introducing constraints. So this is the very nice progress that this work did. It was, I think, before more than 6 years ago, I think, the work. It's called deep image prior, the work. Okay, deep image prior, work by Ulyanov, Vidaldi, and Lempitsky from CVPR. And they say the following. I have the degraded image. This is the only input that I'm going to introduce to my network. That's just the degraded image, nothing else. And I'm imposing an implicit prior in the following way. Same objective that we saw before, okay? The downscaling of the predicted X is going to be similar to the degraded image. However, X should be an output of a convolutional neural network. That's it. This is the idea. And it's going to be like this. This is the convolutional neural network. I'm introducing a noise to the convolutional neural network. And I would like to predict, of course, this output. I'm going to use this objective. And the idea is that the neural network weights are going to parameterize the restored image. The neural network weights are going to parameterize this image into the weights of the neural net. Okay, it sounds weird, but this is the idea. In other words, the noise is going to be mapped to the clean image in a way that the loss is going to be the difference between the downscaling of the clean image minus the degraded image. This is, yes?
You did try also to add the regularization?
No regularization, nothing. The only regularization is an output from a convolutional neural network with a certain architecture. Not every architecture is okay, but okay. This is the idea. And this was the first work that used implicit representation of the signal using the weights of the neural net. And then when you are going to have another signal, another degraded image, you don't have to change the noise. You don't have to change the input. You just have to change the degraded image, and then the weights are going to be different for another prediction, for another task. Okay? Weird, but it works quite fine. And then many works emerged after this and did a lot of nice things in 3D, in 2D, etc. etc.
You have to train many times.
Right?
Train for every picture.
Yeah, exactly. This is trained for every new task, for every picture. This is one of the disadvantages of this work, by the way.
So you compress the image into the weights of the neural network?
In some manner, yes, you can think of it like this. Yes, yes, yes. Okay. So they showed empirically, mainly empirically, because the theory was not very developed there. Then there was some theory. They showed empirically that pre-trained network or large databases are not required. Eliminating the data and the learning process still yields good results for image restoration. And we are going to ask how, and we are going to answer to this question. Actually, the structure of the network is sufficient and imposes a strong prior, implicit prior to restore the original image, the clean image, while taking into the consideration as input, not as input in the loss, only the degraded image, okay? And actually, the structure of the convolutional neural network imposes a strong prior. Let's ask why and try to explain. So why do the structure of the CNN impose a strong prior? Actually, the network captures low-level statistic of natural images. That's the idea. The structure of the network imposes self-similarity within the same scale at multiple scale, making the corresponding prior suitable for the restoration of natural images. And why does it happen? It happens due to the convolutional operator, which is translation equivariant and local at different scales. The mapping of the noise to similar patches happens due to this convolution operator. But we have convolution operator in different scales, so we can say that we are going to have some hierarchy such that the mapping is going to happen in multiple scales. This is the idea. This is what the author explained. And then afterwards, some theory emerged and explained some ideas. Okay. Then after their work, there was a hype of work in parameterization of signal by the neural nets in 2D, in 3D, in continuous function. You will see in these next three classes today and the other two, how the idea is developed. So just like take an example of super resolution. This is a result from the paper. So this is the ground truth. This is the high resolution image after it was graded and then was predicted. So this is the ground truth. You can see some windows here. This is a supervised manner of training between pairs. And you see the results here. And then you see the result of deep image prior. Quite good. Even similar to the ground truth. And when you just take some bicubic interpolation without training, you get a worse result. Okay? It's just an example. So let's try to understand the mathematical problem setting and try to understand in probabilistic way, what does it mean, the idea of the deep image prior, and how the role of the prior is so significant that you cannot neglect it. Okay? So let's try to understand it mathematically. So the idea is the following. We have the clean image that we all know it, it's unobserved. We have only the degraded image and we would like to restore the clean image. Okay? This is an example of denoising. Okay. So, So how we are going to restore the clean image? We can use the idea of maximum a posteriori probability. Anybody here is familiar with this idea? Okay, good. So the idea is the following. Condition on those observed degraded signal, I would like to predict X, which is the clean image, such that I'll maximize this probability. This is the idea. Using Bayes' rule, what you are going to get? I'm going to get this relation, this conditional probability, and this P of X, which is actually is the prior, divided by something which is not very relevant to the optimization, because just a constant, I can neglect it, so I can look at this. Okay. So this is called likelihood, and this is called the prior. This is the prior of the, for example, the natural images, okay? And this is the likelihood, given the clean image, how probable that I'll get the observed image, okay? And we would like to maximize the maximum a posteriori probability. Is this clear? Almost.
No, this is not clear. I'm sorry, because I have a question. We don't have X, we don't have the clean image, right?
Sure.
So how can we find the prior?
Sure, so we are going to predict it. We don't have it, sure. Okay, we are going to predict it. This is the idea. How we are going to predict it, I'm going to show. We are going to predict this one, given this one. That's what we have, and we are going to predict it, okay? Fine?
Okay.
Okay. So let's take an example in order to explain to ourselves how the role of the prior is very significant. Okay. So let's say that this is the clean image, and the only thing that I know that it was degraded by some normal distribution. I don't know the edited noise. I just know the distribution. For example, normal distribution with the variance sigma squared. Okay. So P of X bar given X is going to be with mean X, which I don't know, and sigma squared variance. Okay. Is this clear? Okay. Then what is the maximum a posteriori? The maximum a posteriori is going to be the following. I would like to predict the restored image X star such that this will be maximized. And as we showed before, this is equivalent to maximizing the likelihood times the prior. Okay. And now let's see the importance of the prior. Okay. So this is the a posteriori, this is the likelihood times the prior. And if I'm omitting the prior and I don't use it, and I'm doing what is called maximum likelihood and not maximum a posteriori, because actually maximum a posteriori is like taking the likelihood and introducing some regularization. The regularization is the prior. And if I'm not introducing some regularization, I'm staying with the maximum likelihood. But let's see what happens. What happens is the following. I'll have maximum likelihood here. This is the maximum likelihood. And since the maximum likelihood is just based on the additive noise, which is Gaussian, the most probable prediction is going to be X star. So the idea is that the restored image is going to be the degraded image. Did you get it? Do you understand it? So if I'm not taking a prior, the minimization, the optimization problems boils down to the input, to the observed image, which is the degraded image. So I need to take into account the prior, okay? Are you convinced? Okay. In other words, ignoring the prior, the best estimation of the clean images is the degraded images, which is the input, and this is not a good idea. We need to use a prior. So let's say that we have a prior. Just somebody gave us some prior, and we are going to minimize. So let's try to write the optimization problem. So the optimization problem is the following: are maps of Px given x hat. This is the likelihood. This is the prior, and it is very common to move from here to here because log it's a monotonic function. And I'll take everything into account with a minus sign. I can move from max to minimization problem and using the monotonicity of the log. And then this part is called sorry. Okay. This part is called data term. Okay. The relation between x, which I don't know, and x bar, and this part is called regularization, R of x. Okay. For example, in the case of denoising, the data term is going to be the difference between x bar and the predicted image, which I don't know, okay? Like what we saw before. So this is called the data term, and this is called regularization. So I need to know how to optimize these two terms, the data term and the regularization term, okay? Which is actually, this is the image prior term, okay? These are of x. Clear? Any questions? Okay, let's move on. So, how should I optimize? This is the thing that I want to optimize, okay? Okay, so one way to optimize is to use the regularization of x and to search in the image space. I start from some initialization, and I have been starting from x0, and I rely on this, that this is the search on the image space, and I move to x1, making graded descent, move to x2, etc., till I get something. This is the regular way. But there is another way to employ this optimization, and this is the idea that was used in deep image prior. The idea is the following. I'm going to make a parameterization. What do I mean by that? I'm going to search in the space of the parameters, the space of theta, but I have a mapping between the parameters to the image space, okay? I'm going to do the gradient descent here, and every time I know what is the mapping into the image space, okay? So this is the idea of moving from a regular optimization to optimization in the parameter space, such that I have some mapping between the parameter space and the image space, and actually this is the prime, okay?
The parameter space of what?
Some parameterization, okay? In deep image prior, it's going to be the parameter space of the, right, exactly. So this is the idea. This is the way. This is the two ways to optimize. But what is the idea behind it? So if G is going to be a mapping which is surjective function R, then the two problems share the same global minima, they are equivalent. So what is the idea behind it? The idea that in practice, this is not the case. In practice, you do not get to the global minima, and the solutions are going to be very different because we search over different spaces. However, the idea of this mapping is going to be very useful due to the expressivity of this mapping. In the case of deep image prior, G theta is going to be the neural net parameterized by theta, where the input it's a noisy vector image Z, and this is going to be the mapping. And actually, we do not have now to introduce also the regularization part to this part, this one, because it's already introduced here as a mapping into the data plane. So we can look only at this. And this is the idea in the DQ file. So I have a convolutional neural network with parameter theta, and the parameter space is going to be theta, like you asked before. We drop the regularization term and use instead the implicit prior, which is captured by the neural network. So how do we map the parameter over the neural network to the image? This is going to be in the following way. We fix an input, noisy image, Z. We fix in the weights and varying the, unlike the common practice that we fix the weight and varying the input, here we do the opposite things. We fix the input and vary the weights according to different outputs. That's what we said in the beginning. And every time that we change the output, we get different representation of the new signal in the neural net. This is the idea. Okay. So few lines of pseudocode, initialize with D by uniform noise, solve the gradient descent. Or that is what I did. The gradient descent is solved with respect to the neural net parameters, theta. And then in the forward pass, in order to predict E star, you're going to use the parameter theta and the input Z random Z. This is the idea of the DP modifier. Let's see some results.
So we don't use the network for learning in any way. We just use it as imposing a constraint for
exactly.
Local
information. It's learning per task. It's learning per degraded image. Exactly. That's the idea. The test and the training are the same things. Yes. There is one question that I would like to ask you. How does it come that in the case of denoising, if this is degraded image, the noisy image, and this is the loss, how does it come that the network does not boils down to the noisy image in the loss? Any ideas? It's an interesting question. It's not an easy answer, but I just want to explain it theoretically and empirically. Just wanted to. So there is something which is called inductive bias. Did you hear about inductive bias here in the class? Let's try to understand the. So the question is the following: this is the loss of the denoising. This is the degraded image, the noisy image. How does it that X is a clean image, and I do not boil down to X bar, which is degraded. This is the question. In the paper, which was I think 6 years ago, they did the following empirical experiment and showed the following thing. They took as X bar several kinds of degraded images. They took natural image, degraded image, shuffled image, and noisy image. And look at the loss. When the degraded image is mostly noise, the loss takes a lot of time to the loss to approach zero. When you start from something which is based on natural images, the loss very fastly goes down to zero. Okay. So just to understand the idea, it seems that the neural network is reluctant to noisy images and descends much more quickly and easily towards natural-looking imaging. And the question is why. Later on, after a few years, it was understood theoretically, and I'm going to explain it, the noise is considered as a low frequency or high frequency? High frequency, great. So after a few years, 3 years, I think, or 2 years, I think, there was a stream of works, starting with the work from here, with Ronen Basri and others, and they showed the following thing. If this is your target function, which is composed of actually low frequency and high frequency, and you train your network to predict this target function, then at first the network is going to learn the low frequency, that this is the dark blue that you see here, and only after a lot of epochs, like what you see here, it's going to learn the high frequency part. So in fully connected network, it was shown theoretically using a spectral decomposition of what is called neural children kernel, what is characterized the neural network, that lower frequency component of the target function are faster to converge than high frequencies. And actually, this is exactly what happens here. The noise is high frequency component, and the natural images are relatively low, composed of low frequency component. This is the reason why we do not boil down here to the noisy images, and before we come into the noisy images, we get the natural images. So there is some idea of early stopping criteria, etc., since eventually you will get X bar, but if you stop earlier, you'll get the natural image. So the idea of the spectral bias or inductive bias was shown later also in our group by Amnon and Yoni and others, using convolutional neural networks and residual networks, etc. And the idea is clear today and is explained now also theoretically, not just empirically, like what they did in the paper. Is this clear?
Did we previously use like a comparison of like downsampled image with the?
This is denoising, so you don't have downsampling. When you have super resolution, you have downsampling.
It's different.
Yes, it's different class. So just to recap, deep image prior, take into account the maximum a posteriori approach by having some implicit prior, F theta z, which comes from the convolutional neural network. This is actually implicit regularization, not an explicit one. The input is noise. The weights of the neural net are trained such that they are going to encompass the signal, the weights, and the only input to the neural network is the degraded image. Okay, so this is the idea. So let's see some results, just to have some idea.
The training one more time.
The training is only based on the Z vector, which is a random vector, and the degraded image. This is the only training for this task. Then you are going to have another degraded image. You should change the X bar and you should train your network once again. Okay? And the idea and the idea is that you have a loss that would like to predict the clean image, this one, and this what?
If we don't know.
We don't know. No. Okay. And this is the idea that you would like to get the predicted X, which is a clean image. And the idea is that the way this is done is based on convolutional neural network with convolution filter at multiple space, such that the signal is going to encode it in the weights of the neural net. This is the idea. And every time you have another task, you should do it once again.
I don't quite understand the idea of the inductive bias. Like you say, you fit the long range, long wave features first. Then what's the incentive for the network to keep fitting the short ones if the long ones can't fit the image? noise.
I'm not sure I got it. I'll try to explain again. Okay? When you look at the neural network, for example, fully connected neural network, you can calculate something which is called neural tangent kernel. Neural tangent kernel characterizes in some regimes the behavior of the network. And when you decompose spectrally the neural tangent kernel, actually it's a symmetric matrix, a positive definite symmetric matrix, you see that the eigenvalues of this matrix behave differently for high frequencies and low frequencies. And since the time for converge is related to these eigenvalues, it turns out that the neural network first converges to the low frequency part, and only after many epochs, it can be very long time, it converges to the higher parts, higher frequency part.
Yes, so once you converge to the low frequency parts to fit the main features of the image,
Right.
Then once you already fit the main features of the image, why does it keep going to increase to get rid of the noise or something like this instead of to just match the image?
Because you have this loss, and this loss is going to be 0 when x is going to be equal to x bar, right? So eventually, after many epochs, that's what will happen. But when you do early stopping, somehow, you will go first through the natural image, and only then you will go.
So if we keep going more epochs than
Sure.
what's supposed to, we will
Yeah.
be noisy.
Sure.
And
Yes.
how does super resolution work?
Huh?
How does this apply to super resolution?
The super resolution work actually in a similar way. Okay, you're going to downsample the signal that you want to predict, and eventually, due to the self-similarity patches in the image, okay, due to the similar statistic in the image using the convolutional kernel, we're going to get something that when you downsampling, you are going to be similar to X bar. One point, this is not clear from the paper, is that they are using always the same downsampler, Lanczos sampler, and not something which is related to the kernel that was used to reduce from SR to LR. It's not clear why does it work very nice, but I think it's clear that it works very nice due to the idea that you do not overfit to this X bar, like what done in denoising. And due to this, they get something which is reasonable to the eyes. This is something which is, you made an exercise about this ZSSR, right? Right? So in this ZSSR, you manage to do some, to construct some database. And here you don't construct database. And this is how you move from one scale to the other scale, and this is the way you move on. But in this is how you're supposed to know the kernel that degraded your image. And here no. And this is a bit strange. Okay, yes.
I don't understand for the super resolution, but here your last term doesn't include the high frequency.
No, I'm not speaking about here about high frequency and etc. Forget about the super resolution and high frequency. Just give an example for the denoising. It's not I would suggest that we move on because we have a lot of material to cover. So let's see some results. So we have the denoising the objective, the in-painting objective, which says that in the part which are not missing, I would like to stay the same, and the super resolution objective, okay? So this is the denoising idea. This is the results here, which is compared to, this is classical method, non-local means, BM3D. You can see some, I don't know if you see from far, but you can see some results which is compared to their part, like this, okay? This is, okay? It's not the state of the art, to tell the truth, but also it's a work of a few years ago and things were advanced from then, but it's not the state of the art. This is the in-painting example. You take an image, you degrade it by some letters, and that's what you get. This is deep image fire, and this is the network that was trained. Seems okay. This is again in-painting with this is the quarter image. It's the deep image fire. This is the result of the super resolution compared to total variation prior and without prior, just some interpolation. This is the result. Seems quite okay. And this is another example of super resolution. I would like to move to the architecture. So the architecture is kind of unit, convolution with unit, with skip connection. Actually, they do not say exactly what is the exact architecture. They call it encoder-decoder architecture and not unit, because they have a different number of skip connections.
What's the middle there? It's a skip connection of taking the same thing. It's just doubling, or
I don't know. Maybe I don't know. I'm not sure. Actually, the architecture is not detailed very in details in the paper. So just this is my guess. It's more or less this is the idea. This is the in-painting with very large hole, like what you see here. What they wanted to explain is that the depth is also very important. If the depth is 6, for example, like here, you get better result than if the depth is 2, what you see here, because the receptive field has also significant role. You have to get multiple scale in order to get good restoration. So the depth also has an important significance. This is the ResNet, which is different somehow from their architecture. And also here, it's not very good. And this is unit, not enough. So this is the best result with depth equal to 6, and it's degraded when its depth is equal to 2 or 4. So just to conclude the deep image prior, so the success of supervised approaches is attributed to learn the prior from large databases. In deep image prior, it was shown that the structure of the neural network can encode the signal of the image, and it's useful for image restoration tasks. And actually, what we have shown that the structure of the network imposes a strong prior limitation, slowness, because every time you need to take the image and to do the training and test, and it takes time, and therefore you do not have also generalization. It's training per each task, but actually it paved the way to many nice ideas in 3D, in 2D, and there are a stream of works, thousands of work that rely somehow on this idea of implicit representation of the signal. We're going to dive into it in this lecture and then in the next lecture. And that's what I just said before. Let's take a 5-minute break and move on. בסדר? תודה. This is a result from one of our papers 2 years ago using a deep neural network to solve this problem. And this is the computer vision problem, going from 2D to 3D. What is computer graphics? Computer graphics is the other okay, computer graphics is the other way around. What do I mean by that? If in computer vision we go from 2D to 3D, in computer graphics we go from 3D to 2D. What do I mean by that? I have a model, a 3D model in the space. I have location of cameras, and I want to generate a 2D images. This is called image rendering, okay? And our focus of this part of this lecture is going to be computer graphics and image rendering. This is the new topic that wasn't discussed in this course, but we are going to discuss it now and in the next following lectures, okay? Okay. So what is computer graphics? By the way, anybody heard about computer graphics?
In gaming.
What? What?
In gaming.
Yes, exactly. For example, games, movies, etc., etc. So what is computer graphics? The idea of computer graphics is to render. What is to render? Is to produce photorealistic, the emphasis in photorealistic image formation. What is photorealistic? Photorealistic is the meaning of simulating the physical behavior or physical environment of the light. Okay, let's see in a minute an example. We are going to discuss today classical rendering, and then in the next class we are going to have neural rendering. The idea that we are going to discuss first classical rendering is due to my understanding. And in order to understand neural rendering, you first should know the classical elements and approaches before neural rendering. So let's discuss today classical rendering. So what is classical rendering? The process of transforming a scene definition. What is a scene definition? Cameras, lights, surface geometry, and materials, such that you can get a rendered photorealistic images from this 3D scene definition. Okay? So, like what was said before, graphics is everywhere. Movie production, game engine, medical imaging, okay, etc. So, what is the pipeline of rendering? What is the process of rendering? So, we said that we are going to move from 3D to 2D, but we are going to move in realistically. Okay? So, the input to the process is huge. It includes the camera, position, parameters, etc., etc. The geometry of the object. What do I mean by that? The object in the scene, the different shapes, the different location. We should take it into account. The material is very important because we should know whether this material is absorbing the light or whether this material is reflecting the light. And we need to know the light in the scene. These ingredients are going into a blender of rendering, and hopefully we get some photorealistic image. This is the idea. Let's go ingredient by ingredient and try to understand everything, okay? First of all, I would like just to give you an intuition. What is a photorealistic image? So this image is a render image that just the local illumination was taken into account. What do I mean by that? That just the light that coming from the source like it was taken into account. Do you think that it's photorealistic image? What is missing into your, what something is weird here?
It's like too realistic, it's too clean.
No, think about the ceiling. Do you think that it's indeed black? No. The problem is that only the direct illumination was taken into account, only the light that comes from the source here, and not the global illumination. If you take into account the global illumination, that's what we did. That's the photorealistic. And what happens here is the following. The source emits lights, and the lights fall on the surface. The surface scatters secondary lights, etc., etc. And the idea in rendering is to take into account all the lights emitting, not just from the source of light, but from any surface. And then you get something which is more photorealistic.
Can you go back one slide? So if this is the case, why you see the reflection of the sky of the wall?
No, because it's okay. You see the shadow, you see the reflection. Yeah. It's okay, but you don't see the other scattering that lights the room. It's okay. That's fine because you take the materials into account and you take the reflection into account and you take the mirror into account. That's okay. But for
but the flow is a secondary reflection. With the flow that is reflected in the
this is not. If you shoot light source, you get shown here. It's okay. So let's move on. Okay. So let's speak about the camera very shortly. The model of the camera is perspective projection with pinhole camera model. What do I mean by that? Think about an object in 3D. Think about a box. The image is reflected from 3D to 2D, like here, through this hole. By that the light rays are going to produce into the box, and that's what we get. The characteristic of a perspective projection is that objects that are far look smaller. Okay. Sorry for this every time it interacts with one. And parallel lines are going to meet at infinity. Parallel lines are not going to be parallel in the image. Okay. And also we have a formula. We have XYZ in the 3D space. Okay. And the projection of the XYZ in the 3D space is going to be projected to the image plane in the 2D space. This is the center of the camera. This is the depth. This is the y-axis. X is not illustrated here, okay? And how the coordinate y is going to be projected to the image plane, which is here, only in the y direction. Actually, using similar triangle, you can see that the projected y is going to be the y in 3D divided by the depth, y over z, okay? That's what you see. This is the perspective projection. If you took the course in intro to CV, you are already familiar with it. Should I repeat it or it's clear? It's not very important to the focus of the course, of the talk, but if somebody is not clear with him, I can repeat. Okay, this is the way images are captured by cameras from 3D to 2D. Okay, let's speak about the rendering process and then move on to every ingredient in the. Okay, so in general, the geometry is prescribed by polygons, actually by triangles, and the idea is to project any polygon from 3D to 2D. Okay, it looks like this. Actually, in computer graphics, everything is a triangle. That's the idea. This was before the era of the deep learning. In deep learning, things looks different, but today speak about classical approaches. So the idea is to move from this triangle embedded in 3D. This is called triangular mesh to 2D, and there are two ways to do it. Okay. The one is called rasterization, maybe you're familiar with this, and the other one is called ray tracing. And these are very different approaches. Rasterization, for each triangle, you ask yourself which pixel does it cover, like what you see here. In ray tracing, you shoot a ray from the camera origin to any pixel, and you ask yourself which triangle or primitives you see from this ray. So this is very different. What do you think, which is more efficient? Rasterization is very efficient, yeah. And the other one is not very efficient. The application also, due to this, is very different, okay? So rasterization, for each triangle, which pixel are covered? It's extremely fast, but it's harder to achieve photorealism because you cannot ask yourself, is object A is shadowed by object B, etc., etc. It's more complicated. It's very useful for real-time application. In ray tracing, you shoot a ray from the camera origin to any pixel, and you ask yourself, which triangles do I see? It's lower, but it's easier to get photorealism. It's very good for movies and video clips where you don't have to introduce real-time requirements.
To what degree do you need to know the details of the geometry for this to work properly? Because it seems like you need to have like very fine triangles.
Because if I'm taking this room, okay, and I want to render it, okay, and I have the 3D model, not just, I would like any place in the geometry to be correct and the material to be correct, any edge of the chair. This is the idea. Otherwise, it's not geometric computer graphics. going from 3D to 2D, it's computer graphics. You need the 3D model with all its ingredients. Okay?
It's like a hard problem to just build the
Very hard problem. Yes, you're right. This is the idea that in the classical approach, it's a very hard problem. But also in the neural approach, it's quite hard problem, but there are some simplification due to the neural approach. So if we speak about the approach of ray tracing, then we know where is the light source, we shoot a ray, and here I see an object. And here we shoot a ray, okay? And we understand that the light source is here, so this is going to be a shadow, which is the idea of the ray tracing. And here we have the light source and the object scene and the camera and the geometry. All these ingredients are very important to get something which is realistic. So there are some issues in rendering. Maybe let's do it fast. So there is something which is called the visibility problem. It's clear to you, I'm sure. If you shoot a ray and you have two objects here, the blue one and the red one, so this is occluded by this here, and this is occluded by this here. So when you shoot a ray and you cross some object, you should know which you hit first, the red one or the blue one, and you should take it into account. Okay, this is also an issue in rendering. Let's move to the geometry part. So why everything is used by using triangles, mesh triangle? Triangle mesh, because triangles can approximate almost any shape. They are always planar. They have well-defined normal. It's very useful. Easy to interpolate using the coordinate of the corners of the triangle. Even a point and a line can be, so it's easy to use. Now, the main problem in ray tracing is the ray mesh intersection. I'm shooting the ray and I have triangular mesh, and I would like to ask myself which triangle I'm going to pierce, which triangle I'm going to touch. I can touch several triangles, but somehow I need to scan all the triangles to understand which ray, given ray, which triangle I'm going to shoot. So we need to know how to solve this problem, and when we do it, we can move on. So here is the ray question, and it's capital letters because we are going to use it a lot now. So this is the formula of the ray. This is the origin of the ray. This is the unit direction of the ray, and this is the parameter that describe the ray. Okay. So when I shoot a ray from the light source to the triangular mesh, this is the way I'm describing it. And the idea is the following: if I want to know whether I'm shooting a ray and whether it can intersect a specific triangular, how should I do it? If I shoot a ray and I want to ask myself, what do I need to solve? Do you have any idea? I have a ray, I have triangle, it's a plane, okay? So I need to solve ray plane intersection, right? This is the idea. And need to solve ray plane intersection, ray triangle intersection. And if I'm concluding that I'm shooting this triangle, I should take it into account, because maybe I'm hitting another triangle, and I should know which triangle is first and to take it into account. Because what I see in the image is the first triangle. The other one is going to be completed. It's not simple, but it is done. So this is very naive algorithm to scan all the triangles. There are some way to accelerate this naive algorithm by some hierarchical approach and dedicate. However, we are not going to get into. Let's move on. This is just an example of one frame of a movie, which took 50 hours per frame, although it's not a new frame, but it's just to let you know how much time it can take to make a good rendering. Okay. So let's move on to lights and try to explain the idea. So what is light? What is radiometry? Radiometry actually is the idea of measuring lights. Our aim is to produce photorealistic images. So as you see here a picture, we need to know which color at each pixel, but this is not enough. Red, blue, green, etc., etc. What do we need more than the color? In addition to the color, the brightness, the intensity. This is very important. In a minute, we are going to answer why some parts here look darker than here. Any idea? It's not a shadow, it's related. Any idea why this is darker than this is darker than this?
The angle.
What is it?
The angle.
Exactly, the angle with respect to the surface, in a minute we'll see it. Actually, the final image at every point, we would like to know the color and the intensity of the color. What do I mean by that? If this is the rendered image, I would like to know the color and the intensity of the color. The combination between them is going to give us the image itself. Okay, just to let you understand what is a color, very illustrative thing, why the banana is going to be yellow. The idea is the following: the light is radiometric energy, electromagnetic radiation, and the frequency of lights, of the color of the lights, of the visible lights, are between this and this. That's what we see. It's part of a huge spectrum of lights which we don't see, of color which we don't see. And actually, when you take a picture of a banana, all the spectrum of the visible light is going to follow the banana, but then only the yellow one is going to reach our eye. All other colors are going to be absorbed into the color which is not the color of the banana. This is the way we see the yellow, the banana yellow. Okay. Okay. This is a delicate issue, radiance and irradiance in radiometry. I'll do my best to explain it to you. There are two measures in lighting. One is called radiance and the other is called irradiance. The radiance is the energy which exiting a source or a surface, that's what you see here, L. And the irradiance is the incoming energy to the surface. This is a very, very naive description. I'll try to do my best to explain it better. Okay? So we have radiance and irradiance. It's very confusing. When I studied this field, I was very confused, but I think I made some organization here that will be able to understand. So irradiance is the measure of the energy of the radiant power incident on a surface per unit area. Just per unit area. How much energy is incident on the surface, on the wall, on the carpet, per unit area. What is radiance? Radiance is the measure of the amount of radiant energy per unit solid angle. What do I mean by that? In radiance, you include the direction also. Not just what is falling on the surface, but the direction of the light, you take it into account. Okay? For a certain point, leaving or arriving at a point in space given the direction. Okay? So the idea is the following, and we'll see in a minute in mathematically. The irradiance look at the surface without concluding, without differing the direction, and the radiance taking into account also the direction of the light from where it comes or from how it goes out. Okay, this is the main difference. So I'm repeating in order that you will be with me on the same page. So the key differences between these two measures: radiance includes information about the directional distribution of the light, while irradiance represents the total power received by a surface. Also, the units are different. We'll see in a minute. If you heard about light field, did you hear about light field? About the light field? So light field is more related to radiance than the irradiance. Light field, it's what we'd like to know in environment at every point in every direction in order to get photorealistic images. So let's start with the irradiance. If it's confusing, stop me. So given, for example, a sensor of a camera with sub-area A, we consider the average flux over the entire sensor area that comes from the light, okay? In order to understand what is the irradiance, we take the energy coming to this area and divide it by the area, okay? Phi over A, okay? This is flux density, the incident flux per unit area, per unit surface area. The units are watts per square meter, okay? Is it clear? Okay. Let's move on. So I'm asking again the question, why do some part of the surface look like or darker? This is related to the irradiance that we just defined. So let me try to explain to you. So consider flux P incident on the surface area. So what is the irradiance? P divided by A. Exactly what we just saw. Okay. Now, imagine that I'm taking the same flux P, but now it's flow to a tilted area, not A, but A prime, like this. Okay? And the tilted area is tilted by an angle theta, like what we had heard in the Zoom just before. So what happens now? A prime is larger than A, right? So the same flux is going to be spreaded on a larger area, right? A prime. So the irradiance is going to be smaller or going to be larger than we had before? Smaller, right?
A is a metric, so it's
it's an area. It's just a line. No, just
it's a line.
Just a surface, like this. Surface. The lights come to here to the surface. It's infinitesimally surface.
So what it means to divide B by A?
Divided Phi by A means how much, it's the flux density, how much irradiance I'm going to have per unit area. Okay? So we have the same flux, Phi, but now it's divided by A prime, and A prime is larger than A. So the irradiance is going to be attenuated by cosine theta, this angle. And actually, in general, what we say, it's very important to understand that when the light is coming in a direction parallel to the surface normal, this is the surface normal, then the light is coming to in direction parallel to the surface normal, I'll get the most of the light. But when the light is coming like this, I'm going to have a darker intensity, right? And this is due to the cosine theta that you see here. It's attenuated by cosine theta. And when it comes from here, I'll get nothing. And here, nothing and nothing. Okay. So is this clear? I'm going to maybe put it on the board also. This is called the cosine law or Lambert's law. If this is the surface and this is the normal to the surface, okay? So the light, when it comes in this direction, it's very important to remember it. If it's coming in this direction, I'll get the full intensity of the light, but if it's coming from this direction and this, here we have theta, it's attenuated by cosine theta. Clear? This is the reason why part of the sculpture there are darker. Okay. Now, so far we spoke about flux per unit area. Now we would like to understand how it comes with the direction. So I'm going to split the space not just over an area, but also over the direction. In order to do this, we should remind ourselves what is radiance. So radiance, you know, this is theta L over R. This is the radiance. For in circle, we have 2 pi radians in total. And the same idea is called solid angle, is the ratio of the subtended area of the sphere divided by R squared. Okay? So if this is, okay, if I have some angle here, this is the solid angle, and it's subtended by this area. Then the steradian, its units of steradian is going to be A divided by R squared. And since the area of a sphere is 4 pi R squared, and is going to divide by R squared, then we are going to have 4 pi steradian in a sphere. Are you with me? Or just it's a
The previous one is, I'm trying to understand if I, right. The previous one is the Bergan is basically the illumination back go everywhere, and here the illumination back is depend on the angle.
you speak about this slide?
Yes.
No, I just, this is not related to what I said before. This is just to move on to understand what is radiance. So far we spoke about irradiance, and what we are going to understand what is radiance. Irradiance is related to the unit per unit area. And when you introduce radiance, you should look at the direction, and that's what I'm going to understand. And for that, you use units which are called steradians. Okay, let's tell you. So what is radiance? Radiance is the Stirling agent density of irradiance. What do I mean by that? You have a point in space, and you have a direction, and for this, you say how much energy I have from this point in this direction. And the energy is going to be constant on this way, okay? This is what is written here. So radiance is energy along a ray defined by the origin P and direction W, like what you see here. And since we took the direction into account, it becomes not just watts per meter squared, watts per meter squared per steradian. Steradian is the solid angle that we saw before. That's what we had before, like this. Is this clear, or you are confused? It's okay. Let me try to show you this slide. Okay. So let's try to understand what is written here. Okay, so this is a nice picture because we see here what happens here. This is a point P. This is direction, which characterizes some solid angle, okay, denoted by dW. And I'm trying to understand how much light is falling on this surface. So I have to take the radius into account, point and the ray, and I have it should be attenuated due to the Lambert slope by cosine theta, like what we say. This takes into account the solid angle dW. So the irradiance that is going to fall here on this surface due to this light which comes from here is going to be N times cosine theta times dW. Solid angle, Lambert slope, and radiance. Is this clear?
The light's coming like to the point from it.
Yes, you can exchange it. Arriving and leaving, yes, the idea is it's similar.
No, but also if the source is like a surface, and it's also another.
Saying that the light is coming in this direction, okay? That's what I know. And this is theta, and this is the normal, and this affects the irradiance here. When I'm looking only at this direction, what happens if I'm looking on more direction? It's a good question. So you can skip it. But this is related to your question. Now, I would like to compute the whole energy falling on the surface coming from incoming light from all directions. Why, for example, is it important? If I have a solar energy system and would like to understand what's falling on the surface, I would like to collect all the direction and to understand how much energy I have at a certain direction. So I'm going to make an integral of the radiance, which is this, okay, from the entire direction W to the point P, attenuated by cosine theta. Every time I'll have another theta, dW, over this hemisphere. This will give me the entire energy, the irradiance falling on this surface. And if you think to yourself, also it's okay with the units, the steradian are going to be constant, and we'll we are going to have watts per meter square, which is the irradiance. I know it's confusing, but believe me that this is the best way that I imagined I have to teach it. I don't know if you have any other idea. I would be glad to hear. So any question? Yeah.
What is exactly hemisphere?
The hemisphere, the half of the sphere. Because if light is coming from the bottom part, it's just it. Okay. Now we are speaking about the other part. It's called the materials, and the idea is the following. You should understand. What?
Sorry, in that formula, W that you wrote is supposed to be the solid angle, right?
Yeah, exactly.
But those are not units, right? Solid angle is dimensionless.
Solid angle is steradians.
Yes, but it's steradians has dimension 1, right?
It's steradians. Okay. Let me.
Okay.
Okay.
Yeah.
If you sit at home and carefully look at it, it's okay. So let's move on to material. When we speak about materials, we can have mirror, we can have walls, we can have plastic. Every material absorb and reflect in different ways. And all this should take into account. And here comes something which is called bidirectional reflectance distribution function. Usually we taught this kind of notion in the course in computer vision, but this year we do not have time to teach it, so we are going to have it here. In short, it's called BRDF. Maybe you heard about it. So when lights hit a surface, the way it's reflected from the surface depends on the surface material properties. This is called BRDF. And the idea is the following: given incoming direction WI, how much light should I get in the scattered direction W out, W in and W out? Okay, this is the idea. The BRDF tells us how bright a surface appears when viewed from one direction, while falls light from another direction. Let's take an example. This is the best case. So here we have a mirror, we have a light source, and which comes from this direction and go out exactly in the opposite direction. So the BRDF from this direction to this direction, what is the number? It's supposed to be the ratio between the energy. What is the number? 1. Because the energy is exactly scattered exactly from here to here, because this is the mirror, and the other sides, the other directions gets nothing. This is totally different, for example, from a wall. When I shoot a light to a wall and I'm looking from many directions, this is called a matte material, I'll get exactly the same energy, no matter from which viewpoint I'm going to look at the wall. Okay, and this should take into account when you render images. Okay, this is called matte material, MATT, the word, for example. So let's try to understand what is the idea of the BRDF. Okay, so you have the light which is coming from this direction, denoted by I, and the light which going in this direction. So actually BRDF is a function of the point in 2 directions. And if I take into account that any direction can be parameterized by 2 angles, so the BRDF has the point and the direction, 2 angles and other 2 angles. BRDF is P, WI, WR, like what is written here. Okay? Functions that depend on the point and 2 directions. Okay? So this is the incoming light, and this is the outcoming light. Okay? So if I have some radiance falling from this direction, I'll call it Li, then the surface encounter Li times cosine theta I times dWi. That's what I see here on the surface. And then light is reflected. So what is the BRDF? Is the reflected energy, LR, divided by the incident irradiance, EI. That's what is written here. Okay? And in the case of the mirror, it's going to be 1. Okay? Because the input and the output is the same. And here, the BRDF, the units of the BRDF is 1 over stereo. Okay?
No. What is this? Okay.
P, it's the point
Okay,
here
so it
of the
depends on the
surface.
point, but also should depend on the reflection, right?
Reflection angle, do you mean theta? Yes, of course.
I don't know. Theta I is theta. It's not it's also like as you said.
Any WI will give me another theta I. Okay, that's the BRDF is the function of the following thing. This is the surface normal. This is WI, and this is what is written here, WI. Yeah, this is theta I, and this is theta R, for example, okay? And this is one value of the BRDF. And now I'm going to have another value of the BRDF and another value of the BRDF, okay? Every pairs of direction and a point P will give me another value for the BRDF. BRDF is a function of the point and two directions, the incoming direction and the outcoming direction. Okay?
Set is defined directly by W.
Yeah, exactly. We are right. Sorry for inconvenience.
When you divide that out by EI,
This is the definition of the BRDF. What do I mean by that? I want to know that if the incoming light is EI, how much is going to be out by LR? This is the ratio between the out light and the in light. If everything is absorbed, I'm going to get a 0. If it's like a mirror, I'm going to get 1.
This is only related to how much the surface is observing, or also what type of surface it is.
It's include what type of surface it is, exactly. This,
So, if it's reflected to everywhere or
exactly.
also in there just where. Okay.
In it. Okay, so let's see some example. We have the perfect mirror. This is the incoming direction, into the outcoming direction. Nothing else is going to be distributed. And this, what I said before, it's like a wall, or like a, I don't know. It's ideal diffuse matte surfaces. It's going to be introduced here, and it's going to be spread to any direction, like this. This is plastics, etc., etc. It's going to be from this direction and spread it in this set of rays. And the retroreflected is going to be here and come back here. So it's a science, but itself. That's what I'm trying to say. Okay, so okay. Now we are going to take into account all what we had we did today and to summarize. Okay. So I have a sensor here, and I would like to understand how much light is going to be attenuated in this sensor in this direction. Okay, and I have some source of lights like here. Okay, so and this is the normal to the surface, and this is the point X. What we had before X, and now we have P, and now we have X. This is WI, which stands for each incoming direction. Okay. So how much light is going to be attenuated in this direction to this sensor? I should take into account the incoming light, Li X W WI, from here. I should multiply it by the BRDF from this direction to this direction and attenuate it by the cosine between WI and the normal. and then sum over all the light sources. Is this clear? Should I repeat it? Is this clear? Or it's okay. So the idea is the following: sum all the contribution from all the light sources. This is, by the way, it's called direct illumination, reflection equation. Take into account the BRDF due to the material and the incoming direction, the out direction at this point, and also attenuate the incoming light by the cosine of the angle between the direction of the light and the normal, and then sum. Okay. You can do the same thing like we do with the hemisphere and employ the integral and take it into account like what is written here. Okay. It's the same like before, just instead of the sum, we have the integral. And then I know what is the reflected light. So far we discussed local illumination. What do I mean by local illumination? I took into account only the lights which come directly from the sources of the lights. Okay? And I didn't take into account any other scattered light in the environment. So the image of three-dimensional object depends on its shape, the reflectance property, and the distribution of the light sources. And also the material properties, which are characterized by the BRDF. Note that the reflection equation considers only the local illumination. Light directly will come from the light sources to the surface. However, we know that it's not good enough, okay? Because we need to take into account the whole environment of the lights, like what we saw in the beginning of this hour. And how are we going to do it? So we are going to move from reflection equation to the rendering equation, which take into account all the environment of the lights at any point in the scene to get photorealism. We need to understand, this is called interreflection. When I shoot a light to a surface and the surface reflect the light to other direction, and then the other direction reflect to other direction, this is called interreflection. I should take it into account. It's not an easy task. It's not solved. You think it's really solved. Okay. And this was developed by this person, the rendering equation. And the principles are the following. We say the following: for any given indoor scene, every object in the room must contribute illumination to every other object. So if I have a light, it falls on a surface, and the surface scatters the light, I should take it into account. In his word, there is no distinction to be made between illumination coming from the light source or illumination coming from the surface. Light fall to the surface and scatter the light. And this is the way we'll get global illumination, and we should take it into account. And let's try to understand what happens here. Don't be afraid. I'm going to explain it and to understand what's the problem and how there are going to be studies. So computing the reflection equation requires knowing the incoming radiance from surfaces, like what we saw before, right? We spoke about the reflection equation. Here we have an eye, okay? And we had some light coming from many directions. Okay, this is the surface normal, for example. But we need to know these values, right? What falls onto the surface, okay? However, this is the incoming light, okay? However, in order to understand what is the incoming radiance, we need to know what is the reflecting radiance from other surfaces. In order to understand what happens here, we need to know from where it came from, like what you see here, okay? So in order to understand what falls here, I need to solve another equation of reflecting equation to understand what's exactly fall here. So in order to understand what falls here, I need to solve one reflection equation, and for this, another reflection equation, etc., etc. Do you see the recursive problem? Everybody see the recursive problem? So we have to compute another integral which should have the same question. You have so the rendering equation, that's what is written here, which is very similar to the fraction equation. The only thing that's taking into account the here I said that this is no, but here I say okay, where it come from? I need to compute it. Okay, in order to compute it, I need to make another reflection equation. And this rendering equation is going to be a recursive one. It's going to be very difficult to solve.
How many steps do you need to go up? Like
Till you reach a light source, then you know that you stop. But you have many rays in the environment. So
no, I mean, till you reach a light source, you can be like infinitely many steps, right?
So let me try to explain it, okay? Of course, it's not solved directly. It's solved by some Monte Carlo methods, some approximation. And I guess the following, exactly related to your question. This is the recursive start. You start from the I, and you select a direction, and then you select another direction, and you touch an object and then another direction till you reach the light source. And you do it a lot of time from this eye to this direction, to this direction, to this direction, etc., to you, okay? It's not direct, it's not easy, it's very expensive, and the idea, if there is no analytic solution, it's very challenging to apply recursive ray tracing, and it's something is called the Monte Carlo rendering, and it selects in statistical some statistical manner traces along the environment and compute it. I'm not going to speak about it, just to let you have some intuition. So this is a rendering, and the first image, there is one sample per pixel, and it looks like this. And then the number of samples is doubled. Okay, and then it becomes better and better, and this is the Monte Carlo rendering till you get this image. But now it takes time. It's not a direct solver. Another example, this is direct illumination when the global illumination is not taken into account. And it looks like this, it's quite dark. And then when you take into account more and more traces or more and more tracks, you get more and more realistic images, as you see. So I just want to summarize and to say what is going to happen in the next two lectures. So we spoke about computed traffic, ray tracing, and rasterization. All these modern methods are going to be done with ray tracing and not rasterization, because ray tracing can handle photorealism rendering. We spoke about explicit representation of geometry. We call it triangular mesh. In the next lecture, we are going to speak about implicit representation of geometry, which is related to what we had in the first part of the lecture, the diplomat spiral. And the idea, we spoke about lights and radiometry. We spoke about BRDF. We discussed a local model and global model reflection and rendering equation. We understand it's hard to solve this rendering equation. Its simplification are done by some sampling of Monte Carlo. And next time we are going to discuss neural rendering and implicit representation. And after my lecture, and the next time, Lior Yariv is going to speak about very nice work in this direction. I will give the details in the next lecture. And I think we are done. I didn't believe that we were able to finish, but I did. תודה, להתראות.